I'm going to introduce Peter. Um, our illustrious Peter Moseley. Peter grew up across the street from Caltech in Pasadena. I understand looking out his front door, he could see the observatory there. And it was there that he developed an interest in astronomy, obviously. Peter has a master's degree in mechanical engineering and worked for a small company in the machine tool industry, and then went on to the Hewlett-Packard Company, where he worked on digital signal processing equipment and that was used in vibration analysis and control and laser interferometers used in precision measurements. His later career was in manufacturing related management. In his spare time, he and his neighbor built a live steam railroad in their adjoining backyards. And I'll post in the chat a link to, it's still, you still have that same website, don't you, Peter? Where the video, I can't hear you, Peter. Got to unmute.
As far as I know, it's still up and live, that website.
Okay, I'll post a link to that sometime during the evening, and if you're interested, you can go look at Peter's railroad. Let's see.
It's gone, by the way.
Yeah, but it's a great video. It's a fun video. Okay, in 2016, Peter and his wife Jackie moved to Bainbridge and became involved in Barn. And Peter is now serving on the board of the Battle Point Astronomical Association, and we're really glad to have him on our board. So with that, Peter, take it away.
Okay, let me do a little share screening here. Okay, this is a picture probably lots of you have seen of the Andromeda Galaxy, and it's a very pretty object, and everybody likes to look at that. But I'm not going to spend a lot of time on it. Instead, what we'll talk about is this format. Excuse me. Frank has already set the stage for using Zoom, and the way this is going to go, I'll introduce some content, and then we'll look at some curated videos. So I spent a lot of time finding stuff on the web, and actually you don't need to take this class. You can just spend 40 hours on the web looking at all the material that's already there. But at least we've tried to put it together for you in some sensible way. And then we'll have some discussion after a video, and then we'll go back and do another one. And sort of that's the general way I'm going to go about this. And as you've already deduced, Barn and BPAA have a collaboration. It actually started in early 2018. BPA, the Battle Point Astronomical Association, has a telescope with a 27.5-inch diameter mirror here in Battle Point Park. And it's the largest publicly accessible telescope in the Northwest. And it was built by some amateurs who got their hands on a very nice mirror that the Boeing company had for the Star Wars program. They were very fortunate to get that. And so they did the work on it, Ed Ritchie and his friends, and built this telescope. But it needed some work, and so the BPAA folks came to Barn and said, hey, you got a machine shop, we need help rebuilding portion of this telescope. And so that started a 2-year collaboration. And now we're at the next stage of that, where we're actually trying to share resources to have things like this class this evening and others that we hope will follow, as well as activities within Barn that would relate to telescope construction and automation and electronics and things like that that would be useful for astronomical work. So one of the things we wanted to do here, Frank has a little poll he wants to put up. We'd like to find out how many of you are associated with either of these two organizations or not one. And so he's going to flash this up on the screen, and you get a chance to click a button that says whether you're, is this showing up for you all? Don't know.
Yeah, they're not. Folks are nodding their heads. So
oh,
you
all
can,
right.
Yeah, and I see results coming in. So
all right.
You have 4 questions. Pick one answer. I see 1 question, 4 answers. Pick one of the 4 answers, and when we get to 100% voted, I'll share the results. So are you a member of Barn? Are you a member of BPAA? Are you a member of both? Or are you a member of neither? It's basically what we're looking for. Okay, 81% voted, and that's 18 out of 22. So Peter and I don't count. So 2 people have yet to vote. Come on, folks, get your votes in.
All right. Well,
Okay, that's
that's
going to do
good.
it. So
Thank you very much.
I'm going to end the poll and share the results. So
Wow.
yeah, there we go.
That's really interesting. That's a very useful piece of information for us, because one of the things we're trying to do, obviously, with this is grow both organizations. So the fact that we've been able to attract a lot of people who are not members of either one gives us an opportunity to pitch joining BPAA and Barn. So I hope you'll all give that a thought as you watch this and if you hear more about the organizations. But thank you.
Okay, I'll stop sharing that and I'll post the BattlePoint website in the chat room. You can go there at your leisure and check it out.
Okay, so let's see. Wait a minute. Folks, there's a slight problem here. When I went to that window, it unplayed my thing. All right. So here is the first slide, which is the title of this is the Introduction to Basic Astronomy, and I hope you'll stay through all 4 sessions, but it's a 4-session class. And this first one is about looking up and seeing what we and our ancestors could see without the use of telescopes or any other aids. Session 2, we're going to talk about the aids, the telescopes and their development and how that changed things. In session 3, we're going to talk about the electromagnetic spectrum, a little bit about gravity waves and detectors, and what the physical processes are that they reveal. And finally, in session 4, we'll go looking back and see about the Big Bang and the expansion of the universe. As I've already said, I think half of you know more about this than I do, but we'll do the best we can. So I always like to start off with a little humor. Pickles is one of my favorite cartoons. I don't know if any of you else look at this, but that's Grandpa there listening, and there's chirping in the background. And then his grandson Nelson sitting there, and he says, "What's that noise, Grandpa?" Well, he says, "That's just the stars twinkling." And Nelson says, "Stars?" "Yeah, when I was a boy, I told my parents that I loved to sleep when the window opened so I could hear the stars twinkle. They laughed and told me what I heard was crickets chirping. Well, I don't care what they still, I still like to hear the stars twinkle." So that kind of makes my day. So Neil deGrasse Tyson pointed out that we as humans, we've been around a long time and we've had ideas about how things work. And we've steadily changed those ideas as we've gotten more facts. More people have put their energy and time into thinking about things and using better tools. And so that over time, an old idea have modified and we've improved them. And you can read what he had to say there. But I think it's an important point that we're always finding new things. And even when we are sure, as they were for 2,000 years, that the Earth didn't move, that we might be wrong and there's something new to learn. So astronomy, astrophysics, and cosmology, and these definitions come right out of Wikipedia. So there's nothing to, oh, what happened there? Oh, I'm sorry, folks. That's weird. I'm going to have to reset this for just a second. I have no idea what button I pushed there. All right. So there, astronomy is a natural science that studies celestial objects and phenomena. Objects are planets and the moon and stars and nebulae and things you can see with your own eyes. And then astrophysics is the branch of astronomy where you'll use the principles of physics and chemistry, figure out what's going on, like what's in a star, how are they made up, what are planets made out of, and things of that sort. And then cosmology, as you know, is the scientific study of the origin and evolution and eventual fate of the universe. And that's always a lot of fun to think about. As Frank said, I grew up across the street from Caltech, and I'll tell you a little more about it in a minute, but one of the people I met there was Alan Sandage, and Alan was a graduate student in astronomy at the time, and he was a protege of Edwin Hubble. And so he was carrying on Edwin Hubble's research on the Hubble constant, from which one can deduce the age of the universe. And he really made that his life's work. And he got the Crawford Prize for his work and contributions to that field. Excuse me. And the Crawford Prize is the equivalent of the Nobel Prize in astronomy. And there's a kind of a fun story about that. Nobel's wife apparently took up with an astronomer, and that kind of annoyed Nobel. And so Nobel went and decided that he was not going to award a prize to the astronomers. And so Crawford came along and did that later on. Anyway, Sandage did win that prize, and he was a very well-respected astronomer. He's been dead for some years now. But he told me that the universe is an idea. And if you think a little bit about that, it is an idea. We don't really know what's out there. We have to go and look and try and make a theory and do the best we can to figure out what's there. But it is ultimately an idea. And astronomy is, of course, a big subject. It involves observations, questions. And in science, you need to ask the right questions. Very important, the way you phrase your questions, because if you don't ask the right question, you can go down a rabbit hole pretty fast. The other thing it involves is navigation. Astronomers need to know where to point in the sky, and they developed techniques for doing that. And nowadays we use GPS for navigation as well. But Frank Petrie and his wife sailed around the South Pacific, and I'm pretty sure you used celestial navigation to do that, didn't you, Frank? And but the other thing is that astronomy involves making theories, involves physics, mathematics, quantum mechanics, thermodynamics, chemistry, and biology. We're on our way to Mars now with yet another spacecraft looking for life on Mars. And then it involves art and music and philosophy. And nowadays we're very interested in climate change and using remote sensing for that. That's a big deal, and it affects astronomers as well. They can't see through the atmosphere as well if there's a lot of moisture in the air. Oh, and then astronomy involves the Big Bang. So it's really covers a great big field. And here's Van Gogh's picture, Starry Night. And I always like that one because it has the swirl that you can see here in the middle. And it looks to me like a galaxy's kind of pulling itself together there. And so I've always wondered how he happened to know that. Anyway, back to Caltech. As Frank said, I grew up across the street from that, and this is the Robinson Building, and you can see this dome up on top. And I didn't know it at the time. I was 10, but my next door neighbor, Andy Bacher, his father was the chairman of the physics and astronomy division of Caltech at that time. And my friend Andy knew that there was a telescope in there. And on September 26, 1950, that shutters of that dome opened up, and we were able to go across the street and raise a big ruckus. And we got Alan Sandage and Helmut Abt to peer over the parapet and let us in and take us up and allow us to look through this telescope, which is a 1/10 scale working model of the 200-inch telescope. And that's a really pretty device. And of course, if it's the first telescope you ever look for, it's super magical. At least it was for me. And that model is for the 200-inch telescope. And there's these beautiful drawings in that building at Caltech by Russell Porter of the 200-inch, a whole series of these cutouts that he made. And that's, again, where sort of art enters into this. It's a beautiful, beautiful piece of art. So that night we got to see the moon, and of course it was eclipsed, so it didn't quite look like that, but we saw Jupiter. I actually don't know what other planets were up at that time, but over a course of time, going back and pestering Sandage and Helmut, we got to see a lot of stuff. This is a very recent picture of the moon taken just the other night by Nels Johansen, who's a member of EPA, and he used a 27.5-inch telescope there. And this is the sun, the moon coming up very low in the sky. It was actually appeared lower than the building at Battle Point when he took this picture, so which is why it has this red color to it. So this is, again, kind of elementary, but the thing that's most important in the sky for us is, of course, the sun. It's a life-giving energy. We get our seasons. It's not been an object of worship, and it's the nearest major astronomical object and very important. There's some fun facts about it. It's hot stuff. It's 27 million degrees in the core, 600,000 degrees on the surface. It's 1 astronomical unit away from us, or we are from it. And that's the definition of an astronomical unit. It's one of the ways that oops, I'm sorry, that went by. Well, it doesn't matter. Well, now I pushed the wrong button, folks. I'm sorry. We'll go through this quickly. Anyway, it's 109 Earth diameters, has 1.3 million Earths can fit inside of it. So thinking back to what folks could see centuries and centuries ago, we can still see it now. A lot of us live in polluted areas where things are hard to see the night sky. There's an awful lot of light pollution here on Bainbridge. And but if you were a shepherd out in the Middle East or something, you could look up and notice a lot of things that we don't really get a chance to notice. But the kinds of observations that were made where the sun and the moon and the stars all rise in the east, move across the sky, and set in the west. We all know that. Sun and the moon seem to be in different places in the sky during the year, and we see different stars as the seasons change. And the moon has phases. It goes from a sliver to a full moon. And the sun and the moon are both eclipsed at various times, which means that the moon gets into the Earth's shadow, or the Earth gets into the moon's shadow. And there are wandering stars. The word planet comes from the Greek for wander, so that's one of the ways you can tell the wandering stars are planets. And then the wandering stars are different because they don't twinkle. I don't know if you've ever noticed, but when you're looking at Jupiter, it doesn't twinkle. Whereas if you look at Sirius or some other bright star, you'll notice that it twinkles. So 2 of these wandering stars are always close to the sun, and that's Mercury and Venus. And the one that we call Mars seems to have red color. And there's fuzzy patches of light that don't seem to be stars. And every once in a while, a really bright star appears and then gets dimmer and fades away after days or weeks or months. And finally, there are shooting stars, and now there are comets. And in fact, there's a comet in the sky tonight. Recently, and it's fading though. And this is Frank's picture of the comet Neowise taken from his balcony here in Bainbridge. The other thing people notice were the rhythms of nature. So the seasons, when to plant, when to harvest, these things were all very, very important, still are actually. Seasons related to where the sun rises and sets. And being able to predict these events was really, really important. And so early observatories were made to try and chart the movement of the stars and other objects in the heavens. And people didn't know quite where they were. They just knew they were out there, but they knew that they changed in systematic ways, and they could use that knowledge to plan. And the question is, how do we make sense out of all these observations? People were able to make them very, very long time ago, but what's going on here? And that was the big age-old question. But there's a more current version of it here. We're back to Grandpa and Nelson. He says, wow, look at all those stars. There must be a billion of them. And then Gramps says, whenever I look at the night sky like this, it always makes me aware of my own insignificance. Earl, I need you to come and empty the muffins litter box. He says, sometimes I don't even need to look at the sky to know I'm insignificant. So humans are very well adapted at noticing patterns and change for that matter. And as you know, the ancients devised the system of constellations, and we're going to find out a little bit more about that right now. But looking up, they saw these fixed patterns and assigned significance to them. And if you nowadays, you can buy an app, one like Star Walk 2, and put that on your iPhone and go outside and hold it up, and you can see on your iPhone what you're looking at, and it's all identified. It's all pretty cool. So I'm going to peel off a video here from the History Channel, and we'll learn a little bit about the constellations and what's up there.
From the Latin base co, meaning together with, stella, meaning star, the word constellation means a grouping of stars. Mapped out like a blueprint, constellations are patterns for the billions of stars that are scattered across our sky. Based on mythological stories of Greek gods, creatures, and animals, our heavens have more tales to tell than hieroglyphics at Giza. The meaning and movement of constellations were deeply rooted in Greek culture. Among them, Orion, the hunter, was said to have encountered a venomous scorpion. To escape from the creature, he jumped into the sea, which to the Greeks explained why the constellation Orion appeared from November to March, but disappeared as Scorpius rose to sting him. All of the constellations that we see in our night sky change positions throughout the year. Why does this happen? The Earth spins on its axis, moving east to west, so objects appear to rise in the east and set in the west each day from our vantage point. As Earth continues its path around the sun, different constellations become visible at night, as the sun appears to be in different parts of the sky. There are a total of 88 recognized constellations by the IAU, 12 of which are zodiacs. Zodiac constellations differ from the rest of the 76 because they cross the path of the ecliptic, which is the path that our solar system's planets travel along each year. Because these constellations were so-called touched by the sun, Babylonian astronomers thought they bore significant importance. While viewing constellations, make sure to bring a Greek mythology book so that you can read the many tales of heroism and tragedy that these legends endured in order to earn their place among our heavens.
So we can take a moment now, and you can raise your hands or whatever you want. And we can talk about what we've seen so far. Any comments or questions or...
Okay, any questions, comments? Use the raise hand button if you have anything. Nobody?
I think everybody knows this.
Yeah.
All right. So let's go on. We'll hear Bill Nye talk about what the ancients saw and understood and the great discoveries that were made as a result of the observations and data that was collected over the centuries. This is from the Discovery Channel.
For most of human history, the only light we knew came from the sky. By day, the sun. By night, an uncountable number of stars. From the beginning, our ancestors believed that the sun and the stars were heavenly, out of this world, and they were right. We've been watching the sky for thousands of years, but until recently, we couldn't see well enough to understand our connection to the cosmos. But now, our astronomical vision has sharpened, We can see farther and clearer. We can observe objects that are invisible to human eyes. Our increasingly improving vision has allowed us to make great discoveries, revealing an astonishing and wonderful universe. What follows are 13 of the greatest discoveries in astronomy. Our first great discovery happened over centuries, as the first humans looked carefully at the sky in places like this, the empty, cloudless deserts of the American Southwest, the Middle East, Africa, and South America. Of these ancient astronomers, the most important were the Mesopotamians. They considered the objects in the sky gods, and built giant towers so they could record the rising and setting of the sun, the moon, and the stars. For more than 1,000 years, they used clay tablets to record what they saw. To find out more, I paid a visit to Professor of Astronomy, Owen Gingrich.
Here, for example, is one of these clay tablets. Have a read.
Yeah, these people wrote small.
Yes. I was perfectly amazed when somebody came into my office and picked it up and actually started reading it.
So what language is this?
I think this is in Babylonian. Hundreds of these tablets were unburied. Among these hundreds of tablets is a tablet called the Venus Tablet of Amazadaga. And this tablet contains the motion of the planet Venus. That's the earliest record we have of a planet moving.
After the Mesopotamians made the first records, it was the Greeks who took the next step.
Some of the Greek astronomers made a field trip out to Mesopotamia to find out what had been going on there, and they seem to have brought back some systematic records, so that ultimately it gave the basis for making a mathematical theory of the motion of the planets.
From their observations, the Greeks developed a vision of the solar system that would stand for some 2,000 years. That the planets move, revolving around the Earth. It would take our next great discovery to set the record straight. The year is 1543. A 70-year-old man is dying. His name? Nicholas Copernicus. A doctor and lawyer by trade, but for nearly 40 years he was also an amateur astronomer. A pursuit that had led him to challenge one of the most fundamental and sacred beliefs of his time. As a young man, Copernicus had studied the heavens and found that the Greeks' Earth-centered system failed when it came to predicting planetary motion. He began to wonder if the Earth itself moved.
But here is Copernicus's idea.
With the sun as the center.
The sun is the center, and now suddenly
All the planets
are going always the same way around. They're not stopping.
Copernicus realized that the movements of the planets were better explained if the sun were at the center of the solar system and the Earth circled it like an ordinary planet. It was a revolutionary insight.
Despite any evidence that the Earth was moving, he came up with this book, which gives his new theory.
This idea, this book, changed the world.
Yes, because it made the Earth a planet, and it fixed the sun in the center. If you don't have that blueprint, you don't march ahead to the physics of the cosmos. As it happened, the final pages, which were just these here in the front of the book, came to him on the very day he died. I suspect, I mean, he was lying there partially paralyzed from a stroke. He was probably just hanging in there till he could make sure that it was done.
Everyone, from the Greeks to Copernicus, assumed the orbits of the planets had to be circular. But in 1571, German mathematician Johannes Kepler shattered that assumption with our next great discovery. Lacking calculus, Kepler improvised ways to compute the circular orbit of Mars. The work was tedious. Kepler wrote that he was almost driven to madness considering and calculating the matter. His calculations began to reveal that the accepted notion of planets moving in circles simply did not work. Then a new idea came to him.
Kepler realized somehow the sun had to be driving the planets in some way that he didn't fully understand, and to get a self-consistent picture, he found that an ellipse was the path rather than a circle.
With this breakthrough, Kepler had devised the first method for accurately predicting the movement of the planets and stars across the sky.
When his tables predicted the planet Mercury to pass across the front of the sun, and nobody else's tables were close, that was dramatic proof of the accuracy of his astronomy. It linked the motions of the planets solidly to the sun. This was a very important point to help stress the idea that the Copernican sun-centered system really had physical significance.
Oh, here we go again. Oh, there we go. All right, good. So we have time here to have a little more conversation about this if anybody has questions or comments.
Okay, we've got a question from Emily. Go ahead, Emily. Unmute yourself.
Hi. So when he was making, I just had a quick question about the last thing that we listened to. When he was Copernicus, when he was able to like realize the sun was in the middle, was he able to track the like relative speeds that the planets are orbiting in order to predict that Mercury would cross the sun? That seems like really, it seems like a lot.
Well, it is a lot.
Does this planets orbit at different, I mean, I know the orbits are all different sizes, but they move at different speeds as well. Is that correct?
Yes, that's true. And so a lot of observations were made, and from those observations, later observations had been, I'm sorry, let me back up. Tycho Brahe had made a lot of observations of the motions of the planets. And Copernicus was looking at those and trying to figure out, no, it was Kepler who was looking at those and trying to figure out how he could fit a circle to the observations that had been made, and he couldn't make it work. But the measurements, you're right, the measurements had been made, and it was trying to fit the data to a formula that didn't work. You just couldn't make it work. And it was finally the notion that it was the ellipse was what made it work. But you're right, Emily, that was not taken just out of his imagination. He actually had some hard data to look at and say, well, if I had to go around this circle at such and such a rate, it should be at this angle in the sky. Well, it's not. What's wrong? And so this is deviation between theory and observation that caused him to come up with a different view, which turns out to be the correct one.
Prior to his, prior to him, was the like distance, the relative distance of different objects in the sky known? Like, was it known that they didn't? Okay.
No, they were. Could I jump in, Peter?
Yeah, please.
So it's important to realize that Copernicus and Tycho, neither one of them had access to a telescope. They were using devices not unlike a sextant to measure the positions of the stars and the planets and to track their motion. It wasn't until Galileo took the first telescopes and turned them on the stars and the planets that astronomers started using telescopes. And Galileo was a contemporary of Kepler. So Kepler was in the position of getting more accurate measurements and being able to actually answer the kinds of questions that you're asking, Emily. He was able to discern how quickly the planets were moving, and from that deduce how far away they were and how fast they were going. Okay, any more questions? I don't see any. Go ahead, Peter.
All right, well, let's find out how come we have seasons. Let's see if I can make this work. There we go. And of course, the reason is we have a tilt.
You know that Earth orbits the sun, right? And that it takes a full year for our planet to complete its orbit. Earth also rotates like a slightly tilted spinning top. Earth remains tilted in the same direction all year round as we orbit the sun. But that means the sun's light shines differently on Earth at different times of the year. Let's look at Earth when it's winter in the northern hemisphere. Observe how the North Pole tips away from the sun. This means that sunlight strikes the northern hemisphere at a shallow angle for a short period of time. This is why winter weather is generally cool, with short days and long nights. As Earth orbits the sun, we move towards spring in the northern hemisphere. Now Earth is tilted neither toward nor away from the sun, as day and night are about equal in length. As we make our way to the summer months, notice that Earth is still tilted in the same direction, only now on the other side of our orbit. The North Pole is tipping toward the sun. Sunlight strikes the northern hemisphere more directly, and the sun stays in the sky for a longer time. Compared to winter, summer days are warmer, and the sun stays in the sky much longer. Notice too that while it's summer in the northern hemisphere, it's winter in the southern hemisphere. Because of Earth's tilt, the seasons are reversed. We observed how Earth's tilt creates the different seasons throughout the year. How does this affect life? Plant life and other photosynthesizers, we call them primary producers, depend on sunlight. They respond to the changes in the seasons. Earth-orbiting satellites measure the amount of carbon dioxide absorbed by these primary producers. Bright regions on this map show where they devour the most carbon dioxide, turning light from the sun into oxygen and natural sugars. In spring, when sunshine strikes the cold waters of the North Pacific, productivity skyrockets. Phytoplankton and other microscopic photosynthesizers form the base of the ocean food web, and all ocean life responds to changes in the seasons. On land, forests grow green during the spring, brightening the continents. During winter, continents in this view turn dark from a lack of photosynthesis.
So we're going to now look at a video about the solar system. And again, this is something you all know, but here it is.
Our solar system is one of over 500 known solar systems in the entire Milky Way galaxy. The solar system came into being about 4.5 billion years ago when a cloud of interstellar gas and dust collapsed, resulting in a solar nebula, a swirling disk of material that collided to form the solar system. The solar system is located in the Milky Way's Orion star cluster. Only 15% of stars in the galaxy host planetary systems, and one of those stars is our own sun. Revolving around the sun are 8 planets. The planets are divided into 2 categories based on their composition: terrestrial and Jovian. Terrestrial planets, including Mercury, Venus, Earth, and Mars, are primarily made of rocky material. Their surfaces are solid, they don't have ring systems, they have very few or no moons, and they are relatively small. The smallest and closest to the Sun is Mercury, which has the shortest orbit in the solar system at about 3 Earth months. Venus is the hottest planet, with temperatures of up to 867 degrees Fahrenheit due to an atmosphere of carbon dioxide and extensive lava flows. Next to this world of fire is a world of water, Earth. The water systems on this planet help create the only known environment in the universe capable of sustaining life. The last of the terrestrial planets, Mars, might have also supported life about 3.7 billion years ago, when the planet had a watery surface and moist atmosphere. Beyond the 4 terrestrial planets of the inner solar system lie the Jovian planets of the outer solar system. The Jovian planets include gas giants Jupiter and Saturn, and ice giants Uranus and Neptune. The gas giants are predominantly made of helium and hydrogen, and the ice giants also contain rock, ice, and a liquid mixture of water, methane, and ammonia. All 4 Jovian planets have multiple moons, sport ring systems, have no solid surface, and are immense. The largest Jovian is also the largest planet in the solar system, Jupiter. Nearby is Saturn, the solar system's second largest planet. Its signature rings are wide enough to fit between Earth and the Moon, but are barely a kilometer thick. Past Saturn are the ice giants Uranus and Neptune. The slightly bigger of these ice giants, Uranus, is famous for rotating on its side. Next to Uranus is Neptune, the outermost planet in the solar system and also one of the coldest. Orbiting the terrestrial planets is the asteroid belt, a flat disk of rocky objects full of remnants from the solar system's formation, from microscopic dust particles to the largest known object, the dwarf planet Ceres. Another disk of space debris lies much further out and orbits the Jovian planets, the icy Kuiper belt. Apart from asteroids, the Kuiper belt is also home to dwarf planets such as Pluto and is the birthplace of many comets. Beyond the Kuiper belt is the Oort cloud, a vast spherical collection of icy debris. It is considered the edge of the solar system since that is where the gravitational and physical influences of the Sun end. Our solar system's particular configuration of planets and other celestial objects, all revolving around a life-giving star, make it a special place to call home.
I think all of you know that Pluto, when I grew up, Pluto was the 9th planet, and it was just taken for granted that that's what it was. But there was it got demoted, and it's still a very interesting planet, a dwarf planet. And we recently sent a spacecraft there, and that returned this wonderful image of this really cool, interesting-looking planet. And I'm kind of sorry it's not part of the system, but there is a reason for it. Its axis is tipped. It doesn't go through the plane of the ecliptic like the others, and it also intersects the orbit of Neptune, comes inside that. So it's really a weird thing, and so it's considered a dwarf planet. But I like that picture. So let's jump ahead a minute and let's see how stars like ours are formed. And we have yet another video.
Nebulas house baby stars in every spiral arm of the galaxy.
These regions are the nurseries for new stars. There are young stars in these regions that are heating up gas clouds that surround them and making those gas clouds glow pink.
Stars are made out of gas, basically, and our galaxy has gas.
In fact, our galaxy, you can think of it as having an atmosphere of gas and dust that surrounds all of the stars that we see in the disk. And it's from this gas that new stars are born.
By observing nebulas at different stages in their evolution, the story of a star's birth begins to emerge. It all starts inside a cold, dark cloud of dust and hydrogen gas, where a quiet tug of war begins. The cloud wants to dissipate, like smoke in the air, but gravity wants to pull it together.
They're in a kind of balance between gravity pulling in and gas pressure pushing back out. Gravity wins, and the material crunches down into a disk that is the beginning of becoming a star.
As gravity pulls more and more gas towards the center of the disk, it gets denser and denser and hotter and hotter. Until finally, at 18 million degrees, a miraculous transformation takes place. Hydrogen atoms fuse together to form helium, and with a burst of nuclear energy, a star begins to shine.
These stars eventually get their nuclear fires going in the core, and when they do, they heat up. They can expel the material that's around them so that it kind of clears up the neighborhood.
Over the next few million years, winds blow the surrounding gas into spectacular swirling patterns.
It blows away the gas, it blows away the dust, and it lets us see this beautiful new thing, this place where the star has been born.
Human lifetime is too short to witness the wonder of a star's birth in the spiral arms. But by speeding up millions of years of cosmic time into just a few seconds, we can see one star born after another. Here and there are even more brilliant flashes of light, coming from some of the most violent and dangerous neighborhoods in the entire Milky Way galaxy. Here, stars aren't born. They die.
So, not everything gets blown away, and some material can be left around, and lo and behold, we have our planets. And here we are in the Goldilocks zone, where it's not too hot, not too cold. And on Earth, we were just in the right place. We got liquid water. We can hold on to our atmosphere. It's tipped, so we get the seasons. And that's really a very fortuitous combination of things. And we don't know how often that occurs in the universe, but there's lots of work being done to try and find out. Mars, on the other hand, lost most of its atmosphere and water, and Venus kept itself pretty hot. But you'll hear astronomers talking about their planetary searches and about looking for planets which are in this habitable Goldilocks zone. So, conversation, questions, discussion? Hearing none.
Are people falling asleep on us? There, Carrie Kirk has her hand up. Go,
Carrie.
All
right.
So I know that the tilt is what causes seasons, but does the elliptical orbit have anything to do with our weather? Like, does it make the winter colder or the summer warmer?
It has very little to do with it. The ellipticalness, that's the wrong word, of our orbit doesn't make our distance from the sun change all that much. And the tilt is a much more significant effect. I guess that's the answer, unless Frank has something to add to that.
Well, I can add some numbers to that. The orbit of the Earth, well, one astronomical unit is about 93 million miles, right, Peter?
Yep.
And so the diameter of the Earth is twice that, or about 180.
The diameter of the orbit.
Sorry, the diameter of our orbit is about 180,000 million miles. 93 million, what did I say? 93 million, 180 million miles. Sorry about that. The ellipticity amounts to about 2 million miles. So it's a very small percentage of the total. And in effect, it's insignificant from the point of view of how much solar radiation we get. So the seasons are entirely attributable to the tilt and not to the elliptical nature of the Earth's orbit.
Awesome, thank you.
And another thing about the tilt, well, excuse me, we're spinning like a top. And a top, if you set one to spinning, on your desktop and you watch it, it precesses, it wobbles around like that. So right now, our tilt is pointing right at what we call the North Star. But every 26,000 years, we rotate all the way around and then come back to that same spot. So there's a precession that takes place, which makes it so that the star pattern of the stars in the sky appears to change because the Earth's axis is tilted, and that will affect weather over long periods of time.
Okay, we've got more questions. Emily has her hand up. Go again, Emily, and unmute yourself.
Yeah, maybe, and I maybe just missed it, but when they were talking about how stars are formed, they talked about how gravity pulls the gas towards the center and, pulls it really tight. What is the source of the gravity? Like, what is the gravity doesn't just happen, right? Like, I don't know if I just missed it in the video or not. But.
Well, gravity is a very interesting topic. All matter has some gravity associated with it. And I won't go into the Higgs boson, but that's what physicists have been looking for a long time to explain gravity. But nevertheless, every little molecule has some gravitational pull on another molecule that's nearby. We're, of course, used to that. We're big collections of molecules as humans, and when we drop a pencil, it falls to the floor, and that's the mutual gravity between the pencil and the Earth. So you have these gases all swirling around, and gravity's trying to pull them together. And as they said in the movie, the gas pressure is trying to push them back out. But when you get enough pieces of material collected together, their cumulative effect is to get stronger and stronger and pull in more and more material. And the gas is not impeded by anything. I mean, it's running into itself. There's nothing besides the gas to run into. So the gas can flow into that center spot and then over a fairly long time, millions of years actually, it takes to condense that gas. And then the self-gravity is so strong that it pulls it together to where the temperature in the center gets hot enough for nuclear fusion to take place.
That's really tiny, like molecules, and then just gets bigger and bigger and bigger. Is that how it?
More and more molecules get accumulated in there. There's the cloud of gas that the star is forming in is very large, has lots and lots of material in it, and it gets sucked in by the gravity, and then you get something the size of the sun or much bigger, as we'll see later on, and a huge amount of material flows into that, and the gravity, self-gravity, is pulling it together and just squeezing it like that. And it's that very high pressure that creates a high temperature, which in turn starts fusion, and then fusion releases a great deal more energy and causes more fusion to take place. Meanwhile, more materials falling into the surface of a thing, even though there's nuclear fusion going on the inside. Finally, it gets kind of stable. Our sun is in a pretty stable position, and it'll be around another 4.5 billion years, and then it's going to expand and then go away. It'll become a different object. But that general process is gravity, and gravity is a kind of strange force. It's one of the weakest forces in nature, if not the, Frank.
Mm-hmm.
when you have enough material, and there you're talking enormous amounts of material, then the self-gravity becomes a big effect.
Okay. Ginger has a question.
Actually, it was Jim.
Jim has a question.
And Peter, the tilt of the Earth is at a certain angle to its orbit, and other planets have a different tilt to their orbit.
Correct.
Have the physics of why those tilts are at those particular angles, has that been worked out?
I don't know the answer to that. I think it's fairly local and random how it came out. It's all related to the conservation of angular momentum. As things collapse down, there's a certain amount of angular momentum in the neighborhood of all this gas or rock or whatever it was that's forming the thing. And the axis of that angular momentum gets conserved, and it stays at that angle once it's collapsed in on itself. Now, the Earth, for example, we think the moon may well have come by the Earth having been swatted at some point by a Mars-sized another planet that was forming, and we collided with it, and the moon formed out of that mess. That may be one of the reasons we have the tilt we have. I don't think I've never heard anybody say for sure, because you can make up so many theories about the moon. But the latest ones that I've read about, and somebody here else may have more information, but the collision that produced the moon may well have had something to do with the tilt. Frank, maybe you know better.
Well, and that's exactly right. The current thinking is that the collision with some sort of a body, as Peter said, created a mess, and out of that mess coalesced the Earth and the Moon in their present relationship. Or other planets have different tilts, and the thinking is that they were the victims of different of collisions that had different geometries that caused different tilts, and so so it's all pretty random how that comes out. There's no overlying physics that controls all of them in the same way, other than the physics of collisions. Is that helpful, Jim?
Very much. You guys are on it. This is wonderful.
Okay, thanks for that. We got one more question. Rick, go ahead, Rick. Unmute yourself.
Yes. Sorry. I have two questions. One is in the formation of the solar system, or of solar systems in general. Once the star begins to form, is it the photons from the star that then clear away the area, or what is it that clears away the area around the forming star?
Well, it's photon pressure, but it's also gas pressure. The sun's surface gets very hot, of course, and so that material that's banging around on that surface, some of it just has enough energy to leave the surface of the sun in spite of the gravity and head out into space in a sort of a spherical shell away from the surface of the sun, and then it bangs into other things and pushes that further away as well. So you have what we now know as the solar wind, which we're flying through the solar wind all the time. It's this material that's being ejected from the surface of the sun, and it's electrons and protons and photons, and so it's essentially hydrogen nuclei primarily. But that stuff was falling in, and then when things got hot enough, it began to be pushed back out. So there's a cycle to this where the gas falls in, it's relatively cold gas, and gravity is the main effect. And once that fusion takes place and enough energy gets out of the center of the sun and onto the surface, it radiates, well, it blows away and makes a solar wind, and that's what kind of cleans things up. Strips off the atmosphere of Mercury, and although Venus is our size and it held on to its atmosphere, but a lot of other junk that might have been there and gas that might potentially have fallen into the sun is pushed out.
Yeah, okay. The other question I had is thinking about the Jovian planets, and if you consider the rings around some of those, how dense are those rings? You know, when you see these science fiction movies, they're dodging between things, but my guess is that they're not that dense.
They're not very dense. I think the Cassini spacecraft flew at least between one of the gaps in the rings, didn't it, Frank?
Yeah, yeah, that's right.
I don't think they risked going through a ring. The density, probability of hitting something, and the value of that spacecraft that made that not a worthwhile experiment. But it is pretty. It's not very dense. You notice on that one movie that it's 0.6. It's 1 kilometer thick, which is very thin, and it's mostly ice and probably some rocky material, but it's primarily ice, I think. And even so, if you're a spacecraft and you run into a ball of ice, even if it's not very big, it's gonna be a bad event. And then they didn't realize there were rings around the other Jovian planets until quite recently, but they've been able to spot them. The ones on Uranus are most distinctive. But it turns out all those guys have that. And in a way, that's sort of the same thing, where material that fell into those things, into those gas giants, left behind some other material which formed into a ring in the same way that the planets formed into a ring around the sun. And that's the leftovers. Some of it also may have been captured gravitationally from coming in from the Oort cloud or someplace like that.
Yeah.
So I just did a quick search. The density of the rings, I might have to read this article to know if what I'm saying is really correct, but it appears that the density of the rings is about half the density of water.
Oh.
Maybe a little less than that.
Yeah, that's higher than I would have guessed.
It's mostly ice. It's mostly ice particles and some dust and rock, but there's a lot of open space between the chunks.
If it's mostly ice and it's half the density of water overall on average, then that means maybe that somewhere approaching half of the space is taken up by stuff.
I would agree with that assessment. Yeah.
Sounds about right.
Yeah.
Okay. Any other questions? Jim, you got another one, or Ginger?
Yeah, here we are.
Yeah, I can.
The Jovian and terrestrial planets, do they have any understanding of how those became so different from each other?
I don't know as I've read this or seen it, but in general, you can think of it as, remember how they, once the sun gets going, it wants to push out and start blowing away the gas. So there might have been some gaseous blobs in close, but they get pushed out because they're not dense, and the gas that might have formed them gets pushed away. And so you have to be out a distance away from the sun in order for those gas giants to form. Although we're discovering planetary systems where they do have gas giants very close to the star. So that sort of defeats my discussion there. The only other thing I can say is that lots of stars form in different ways with different kinds of the general process is the same, but the makeup and the rate of formation and all that is different from location to location. And so you can get this variability. But my guess is that the gas-rich area near the sun, most of that gas fell into the sun, and the stuff that's farther out had chance to form into its own spheres and become Jupiter and Saturn and Uranus, out further, because that material was not pulled into the sun. Frank, you want to clarify that for me?
Yeah,
I just made that up.
No, that's good. That's good, Peter. That's good. And it's just colder farther out, and so the gas can survive out there and it's not energized. It's not heated up to the point where it wants to run away from the molecules want to run away from each other. They're okay being pulled together by gravity because it's so cold out there. Um, that's one of the reasons why Pluto got demoted, because it's clearly not a gas giant. It clearly doesn't belong out there as a rocky planet.
Poor thing.
And of course, the rock enclosed, the rock can survive the heat of the sun.
Okay, thank you.
Yep. Anything else? Oh, Gail has her hand up. Go, Gail.
I wanted to know what the Oort cloud or Oort belt is made of.
Almost all ice, as far as we know. I think it's primarily ice, and you might wonder why there's all this water that can form ice, but that means there must have been a lot of oxygen around, and the way the oxygen was not in the early universe, and it showed up later as a result of supernova explosions where stars, we can have this as another whole class, but stars of a certain size, when they form, they will ultimately collapse on themselves and then explode. And when they do that, they form all the heavier materials up through iron, and that includes oxygen. So then there's a chance that in a second or third generation star, which is what ours is, that there will be oxygen around. And if there's oxygen and hydrogen, then you got the opportunity for water. And then you get out where it's very cold, and the water is, of course, ice and not vapor. And so the Oort cloud is a very cold region that has a combination of oxygen and hydrogen tied together in the form of water. But it's quite far out, very far out. Somewhere I think I've got, probably in the second show here, we talk about the astronomical units and how far out the Oort cloud is, but I think it's 158 or more than that even. It's a long way away.
Yeah, and that ice is not just water ice, but it's also carbon dioxide ice, dry ice, if you will. And there's also dust in those bodies. And every once in a while, one of those bodies will be perturbed from its nearly circular orbit, and will be launched into the inner solar system and as it comes close to the sun, it heats up and grows a tail, and we call it a comet. And we just saw one of those not a couple of weeks ago.
You can see one right over Frank's shoulder there.
Yeah, that's
nope, the other way, shoulder.
The other shoulder there,
yeah,
right there. That's Comet Neowise is a visitor from the Oort cloud.
Peter, in your explanation, you referred to the Earth as a second or third generation planet. What's that?
I meant the sun, not the planets.
The sun. Maybe you said the sun.
Because the very earliest stars only had hydrogen and helium available to form stars right after the formation of the universe itself in the Big Bang, which we'll talk about in another one of these sessions. But so those stars were all pure hydrogen stars that then created helium and carbon and some of the other elements. And then when they blew up or ended their life, they distributed around the universe other heavier materials all the way up through iron. And you have to look at your periodic table to see what they all are, and I can't recite the table to you. But anyway, that was the first generation stars. Then the next ones made use of those heavier materials. So they had oxygen and carbon and other material available, and they incorporated those into stars, and those became, is it population 2 stars? And then there's population 3, which are made up the remnants of those. So there's a cycle.
It's actually the other way around, but
is it?
Population 1 are the stars we know today.
Okay.
Population 2 are the earlier generation, and population 3 are the earliest of those.
Yeah.
They got it backwards for some reason.
Yeah, I don't know why. But anyway, it is backwards. But my point is that there's this continual process of formation, and destruction going on in the universe. Doesn't just happen here on Earth. and so we're made up of stardust ourselves. Everything in our bodies came from supernova explosions. We wouldn't be here if this was a pure hydrogen star that we were going around. There wouldn't be any rock. There wouldn't be any of this stuff that we take for granted.
Okay, Peter, carry on. And the time check here, it's 8:15. So
All right,
I
we're
don't know how
doing
much. Doing good?
well. Yeah, we got just. I'm on slide 42 of 48, so we'll move right along. So, question is, where do we fit in all this? So I've got a kind of a fun, buzzy here slide that or picture. So we have a chance here for any more discussion if you'd like.
That's a great final video there, Peter.
Yeah, so all I want to do now is just kind of wrap up by talking about astronomy as a science and go back to what I started with at the very beginning. Asking questions leads to new ideas. And apropos of somebody's comment, the theory comes from people like Copernicus, who came up with the heliocentric model. Remember, before the ancients had said the Earth was the center of the universe, which is sort of, just like every child knows they're the center of the universe. Well, us Earthlings were pretty sure of that until we found out we weren't. And then Galileo's made observations, and then the cataloging. These are all things that take place in science. You ask questions, you develop a theory, you make observations, you catalog, you notice the patterns, in this case, mathematics, was applied by Johann Kepler. And then you develop some sort of an explanation or a testable theory. And Isaac Newton came up with his theory of gravity, along with a lot of other important observations in mathematics. And then you have this theory, you make further observations, and you see deviations, and you're back to asking questions of why is there this deviation? And that led Einstein to try and come up with his theories of relativity, because they were observing Mercury, and Mercury did not follow the orbit that they thought it should follow. And so that was a deviation. And why was that deviation there? And Einstein's theories of relativity were able to help explain that, in fact, very positively explain that. But we're not going to go into that right now. So summing up, what we've talked about is seeing and noticing things, early observations or observatories, covered the constellations, the early history of astronomy, solar system, and our place in the cosmos, which was that last video. And so here we are for discussion and feedback on the whole class and whatever, but the next class is going to be on astronomy, the extending the eye, the history of telescopes and what they do. So next week we'll talk about that. But are there any questions or comments? If any of you are still awake.
So Ginger or Jim, one of you two has a question. I see another hand up.
So Peter, two of the most wonderful concepts in the whole field are dark matter and gravity. Will you deal with those in the future?
Somewhat, not in great detail, because I was trying to, this is a sort of a brief introduction to astronomy and not into the modern stuff. We can do that as another talk, or if there's time, I'll fit it into one of them. But of course, there's a whole raft of stuff which really should show up in this session 4, looking back on the Big Bang and the expansion, because that all fits in there. And if I'll take your question into heart, and I'll see whether I can fit in a little bit about that in there. But that's more advanced than this class was going to be, although it is the modern topic and topic of great interest.
Thank you, a huge thank you. This has been very interesting and informative, and it's obvious you spent a lot of time putting a lot of information together here, and it's greatly appreciated. Thank you very much.
Well, thank you. Doing this, you never know who your audience is going to be. And so in some respects, this is aimed at 5th graders. In other respects, it's aimed at, I don't know, anybody who likes astronomy like I do, I guess.
They can always learn from reviewing and all that, but the pictures and all the videos are pretty stunning photography. Thank you very much.
I think you're going to take us to the 6th grade, Peter.
Okay, well, that's next week.
Yeah.
Yeah, next week we get and then 7th and then 8th, and then we'll go on from there. Actually, that's something I want to point out. We hope that what we'll be able to do is this is begin to be a series of similar type of activities where Barn and BPAA collaborate, and we have more of these kinds of things going on. There's a lot of interest in astronomy, and it isn't the only subject, and as we've already talked about, it branches out into physics and all kinds of technical stuff. In fact, Jim Thrash should give a talk on how he helped build the Laser Interferometer Gravity Observatory, and so he's a major contributor to astronomy himself.
Thank you, Peter. Or you can give him a thumbs up too if you want.
Okay, well, thank you all. This has been a lot of fun.
Look forward to seeing you next week.
Next week, yep.
Thank you.
Great. Thanks, everybody.
Great job, Peter.
Thanks.
Thanks, Peter.